All right, so let's continue our discussion of the basics of thermophysical properties in steam tables by looking at the phase equilibrium diagrams. So again, a reminder, the phases of a pure substance are going to be either solid, liquid, or gas for our purposes. Again, we're not worrying about things such as a plasma. When the gas could be slightly cooled or compressed and form a liquid, we usually call it a vapor, not just a gas. Now, substances can be either pure or a mixture. This course is going to focus on the pure substances. Technically, a pure substance is going to be composed of only a single type of molecule. However, we will occasionally treat things as pure when they're a mixture that stays completely in a single phase. So, for instance, air we might call a pure substance, even though we know it's got both oxygen and nitrogen and a whole bunch of other gases mixed in. Let's look at basic phase diagrams. So these are pressure temperature diagrams. CO2 is typical of most chemicals. Water is a little bit unusual. There's only really one significant difference between these. But they all have sort of the same general shape. So let's identify these points here and make sure that we know what they all mean. So first of all, the triple point. The triple point, well, if you look at this curve, you'll see that we've got solids off to the left, we've got liquids kind of top more to the right, and gases are the bottom portion of this graph. And each of these regions are separated by curves. The curves represent where, say, this curve is where solids and liquids are in equilibrium. Okay, they both can coexist. Liquids and gases here, and solids and gases here. All three of those curves meet right here at what's called the triple point. The triple point is a unique pressure and temperature for a pure substance where all three phases can coexist. Now the critical point is going to be another unique point for a pure substance, and it is the top of the liquid vapor curve. Okay, and the critical point is the highest temperature and pressure where you can have liquid and vapor both present simultaneously. If you go to higher temperatures and pressures, you reach something that's called just a supercritical fluid. Sometimes we'll call it a supercritical vapor, gas, sometimes a liquid. The point is, it's just simply a fluid. It has properties that are partly like a liquid, partly like a gas. The names of these curves where these two phases coexist, where liquid and gas coexist, is usually called the vaporization curve. Where solid and liquid coexist is the fusion curve, and where the solid and the gas coexist is the sublimation curve. Now the main difference between a CO2, or most substances, and water is the slope of this solid liquid, or the fusion curve. And the slope of that is going to be different, but otherwise they all are pretty much the same, just minor differences. We also can look at how pressure or volume, or pressure or temperature change with volume. And here what we're going to see is the characteristic shape is that there's going to be saturated liquid forms a curve. Saturated vapor forms a different curve. They meet at the critical point. Again, that's where the liquid and the vapor, it's the highest place where they can be separate phases. So this is where they come together, those two curves. This region created under here, the dome, is a liquid vapor saturation region. So you have both liquid and vapor. And as the volume changes, you go from very little vapor to almost entirely vapor moving across here. This side of the diagram is the compressed liquid region. This over here is going to be superheated vapor region, or just a gas. And above here is that supercritical or a dense fluid. Okay, again, that combination. If you put these things together, you can see that they are all interrelated. And so if this diagram helps you with your understanding, great. I do better with the two-dimensional diagrams, but I just really want you to see that these are all interrelated, and that as one is changing, the other two are both changing. Now we're going to be talking shortly about properties of pure substances. And a property of a pure substance is going to be well defined whenever I have two independent properties. In a single-phase system, you can choose any two properties. A lot of times we tend to choose pressure and temperature because I have a good handle on how to measure those. In a two-phase system, pressure and temperature will be dependent. Remember, there's the curves on the diagrams. So I can choose pressure or temperature, and then I'll have to choose some other property that will tell me relatively how much is in each phase. If I happen to have that three-phase system, remember pressure and temperature are dictated by nature. I don't get to choose those. So if I have three phases, I'll need to choose any two other properties, and those will relate to me how much is in each of those three phases. So we're wanting to be able to find properties, and a lot of times we know the substance is a gas, and we've talked about this in previous courses. So when the substance is a gas, a lot of times I assume it's an ideal gas. Now, an ideal gas technically doesn't exist, but it's a reasonable assumption whenever I have really small molecules. And if they're round and they are not going to interact with each other, so nonpolar typically, then those are good candidates for being an ideal gas. It's going to be better when the pressure is low, high, and when the temperature is high. Typically, systems that we get to assume are ideal gas-like are going to be nitrogen or oxygen systems, carbon monoxide, carbon dioxide, methane. All of those are going to meet that small, round, non-interacting standard. If that's the case, then I can use the ideal gas law. So PV equals nRT is what we've kind of always grown to know and love. I call it PIV-NERT. Okay, and R is that ideal gas law constant. If you happen to be in SI units, then 8.3145 kilonewton meters per kilomole Kelvin would be the correct units for R. Now, I can, frankly, put this in mass. PV equals mRT, but then R is mass dependent. So I need to know what the molecular weight is of that molecule. So sometimes you'll see people do this, and it just simply means that we're going to have to correct the units within R. I can divide through by either N or M and end up with PV equals RT, okay, where this is the specific volume, volume over mass, or volume per mole. So that's called molar volume. And so this would also be true in this particular case. If I'm doing it on a mass basis, then R is going to be dependent on the type of molecule and the molecular mass. But a lot of times I'm going to be applying this to closed systems. And if I have a closed system, the mass or moles are going to stay constant, and R is a constant. It's the ideal gas law constant. And so if that's true, then PV over T will be constant. And so at state 1 and state 2, I can say PV over T is going to equal each other, whether I use total volume or the specific volume or molar volume. Now in the next video, we're going to discuss ways of estimating other properties for ideal gases. So if it's not a gas, how am I going to get the properties? We're going to have to look up data. In the Smith, Finesse, and Abbott book, there is water data available in Appendix F. That's really the only big data table they have. Within the course, I have provided a set of data for propane. Okay, it's just an Excel spreadsheet that summarizes that data. If you have other textbooks, you probably have a lot of other data available there. Or one other really terrific resource for chemical engineers is the Perry's Handbook. Now, Perry's Handbook is a big, fat book, and probably most of your faculty will have a copy of it somewhere in their office. So you can get it there. You can get it in the library, but you also have access to an online version of this if you join AICHE. So I'm going to put in a really short plug here, but AICHE membership is free for students. So if you go to aiche.org/membership/students, and I've got a link on our course website, then you actually will be able to join this. And then once you do that, one of the resources is this Perry's Handbook that has data for all sorts of chemicals. Now, the key thing that we're going to be talking about shortly is that I need any two properties to define the state, and then everything else is in the table. Okay? So the first thing I'm going to have to do is figure out what phase it's in. If it's just solid or just liquid or just gas, then I'll look in the appropriate part of the table and read off the data. If it's a combination of liquid and vapor, then I'm going to need to determine the ratio of liquid to vapor in each phase. Now that's going to be called the quality.